Welcome back to our Introduction to Differentiation Formulas. Now, one of the questions that I'm often asked is, well, what is all this calculus good for? And that is a question that, of course, I tried to answer already in that introductory presentation, but it is a fairly hard sell because a lot of the applications of calculus are so sophisticated that you basically need to know calculus before you can fully appreciate them. And some other applications are quite frankly a bit artificial. For example, even though linear motion is important, and even though we have used linear motion to motivate the derivative, it is a bit of an abstraction because most people in the real world don't just go on a straight line, or if they do, then they don't go on a straight line for a very long time. Ultimately, they have curves, and of course, then you will need more sophisticated tools than just single variable calculus. Optimization, however, is one of those subjects where we can get very, very close to the real-life specifications of an important application, namely the design of soda cans, specifically the idea that those things should be designed in such a way that they use as little material as possible. And that's one of the things we'll see in this presentation. So let's get to it. Okay, so what is optimization? Well, basically the idea is that there are quite a few problems that don't just have one solution. For example, there are infinitely many ways to design and shape a soda can. You could make tall and skinny cans, you could make flat and wide cans, you can make cans with all sorts of wiggles in them. Well, what we're then often interested in is among all these possibilities, we'd like to have the best possible solution. And how do you define what best possible is? Well, it depends on the context. But for example, when we're looking at the best possible shape for a soda can, well, then a typical way to define best possible would be to look for solutions that minimize or maximize a certain parameter. For example, the best possible shape for a soda can should use the smallest amount of material because conservation of resources and preservation of resources is certainly something that is very important in this day and age and will stay important for people. And this is then also, let me cut into this, this is also then actually a win-win proposition for industry, because if you use the smallest possible amount of material, that also means you have to buy less raw material in order to manufacture these cans, which means you are saving some money on the manufacturing end. Okay, values that can occur in applications are usually restricted to some kind of an interval. For example, a radius has to be always positive, and there might be other restrictions like budgetary restrictions. So lengths cannot be negative, a radius is a length, right? And there may be other limitations on budgets and so on. Optimization, if you want to put it in a nutshell, is just the determination of the largest or smallest value or values of a function on an interval. And the way in which these things then are optimal depend on the interpretation of what the function does. A largest value may be optimal when you're trying to look at profits. A smallest value will be optimal when you look at resources or at expenditures. Okay, so the abstract definition then, I think we've had that before, but we might as well recall it here. If you've got a function, and d is a set of real numbers on which the function is defined, then a number y sub m is called the absolute minimum value of the function in that domain, if and only if there is first of all a place where that value is assumed, so f of xm has to be equal to ym somewhere in the domain. And for all other values x in that domain, we have that the function gives you a value that is at least as large as the value f of x sub n, which is this y sub m, this absolute minimum value. Similarly, you can talk about absolute maximum values. An absolute maximum value must be assumed somewhere in the domain, so there's got to be an xm, so that f of xm is ym. And it must be so that for every x in that domain, we have f of x being smaller or equal than this absolute maximum value, this f of x sub n. A value that is an absolute maximum or the absolute minimum is called an absolute extremum. And absolute extrema are relative extrema, or they occur on the boundary. Basically, those are the only possibilities, because certainly if something is an absolute maximum value in the whole domain of the function, then it is also an absolute maximum value in a small interval around where it occurs. And then the only other thing that could happen is that the function could be going up and running into the boundary, and that is not something that we typically identify as a relative extremum, because the function might be continuing, and we'll see that in our first example, in fact. Okay, so finding the absolute extrema for a function, what do we need to do? It's another algorithm, really. We first find the critical points and the boundary points. And the boundary points could be infinity or minus infinity if your domain comes in from minus infinity or goes to plus infinity. And then you find the values of the function at those points that we specified in number 1. And if an infinite point, or a point where f is not defined, is among these points, then we would compute the limit as x goes to infinity or as x goes to minus infinity, or the left and right hand limit if these are points that are inside the domain where the function is not defined, or if it's not defined on a boundary point that is not infinity or minus infinity, we would also compute one-sided limits there. The largest of those values that we find in number 2 is the absolute maximum. The smallest value is the absolute minimum. And if these values include infinity or minus infinity, say if we had to compute limits, well, then the function does not have an absolute maximum or minimum, respectively. It doesn't have an absolute maximum if infinity occurs, and doesn't have an absolute minimum if negative infinity occurs. Okay, so if we're looking at something like finding the absolute extrema of negative x cubed plus 3x squared plus 9x plus 1 on the interval negative 2, 2, well, we find the derivative, which is negative 3x squared plus 6x plus 9, right? Then we set that equal to 0. And, well, we have a common factor 3, which we can cancel. That will make the quadratic formula a little bit easier. So we end up with negative x squared plus 2x plus 3 equals 0. But I think here I even just use the quadratic formula. We end up with negative b, negative 2, plus minus square root of b squared, 4 minus 4ac. 4 times negative 1 times 3 is 12, and we've got two negative signs, so we end up with 4 plus 12, divided by negative 2. And that ends up being negative 2 plus minus square root of 16, which is 4 divided by negative 2. And so with the plus, we end up with 2 over negative 2, which is negative 1. And with the minus, we end up with negative 6 over negative 2, which is 3. And yes, this could have also been found with factoring, but as I always tell people, the quadratic formula always works, and so rather than potentially being on a wild goose chase if you don't see the factorization immediately, just use the quadratic formula. It's just math, right? I mean, we just do the algebra here and we get it. Now, a nice thing here, or something that is important, is 3 is not in the interval from negative 2 to 2. So even though the function has a relative extremum there, it is not in the interval under consideration, and therefore we don't need to worry about 3 at all. And that means we only need f of negative 2, which is 3. Let's see, does that work out? F of negative 2. Negative 2 cubed is negative 8, with another negative sign gives us 8. 2 squared is 4, times 3 is 12, and 12 plus 8 is 20. Negative 2 times 9 is negative 18, so you end up with 20 minus 18, which is 2, plus 1 is 3. All right, mental arithmetic, I can still do it. F of 2, let's see if I can do that without already knowing the result. 2 cubed is 8, so we get a negative 8. 2 squared times 3 is 12, so we get 12 minus 8, which is 4. 9 times 2 is 18, plus the 4 that we had from here gives us 22, plus 1 is 23. And that's right. Good, good, good. And let's see, we need to also worry about negative 1, and that should not be that bad, right? Negative 1 cubed is negative 1, with the other negative gives us 1. Negative 1 squared is 1, plus 3 times 3 is 3, and so then 3 plus 1 is 4. It's horribly sophisticated mathematics here. 9 times negative 1 is negative 9, plus 4 should be negative 5, plus 1 is negative 4. Yes! All right! Well, okay, so that means now the largest of these values, which is the 23, should be the absolute maximum, and the smallest, the negative 4, is the absolute minimum. Yes, the absolute minimum value is a value of negative 4, and it's assumed that x equals negative 1. The absolute maximum value, which is 23, is assumed at x equals 2. And that is pretty much the verbal answer to this problem. And remember, we can always check this. We can just draw the function. We've got a maximum here, a minimum here, but remember, the domain under consideration only goes from negative 2 to 2. And that means that our minimum really is at negative 1, and the value is about negative 4, which we can see also here graphically. The value is negative 4, and graphically that is reflected in this. Our other value, our maximum value, is assumed on the boundary, and it really is not a turnaround point as we're used to, but that's because the domain is restricted. And the phone rings. Okay, we were interrupted here for a minute, but we were almost done with this picture. Unfortunately, when I got interrupted, I didn't hit pause, I hit stop, so we've got a separate video here. The last point that I wanted to make about this one is about this relative maximum at 3 here, which, well, basically, for the purposes of this problem, it just might as well not be there. We don't have to worry about it at all, and I'm trying to indicate that with that little explosion here. I was getting a little cute with these things. What you want to remember here is I may be crazy, but I'm not stupid. The problem is solved correctly. Okay, let's move on. The next question already connects to the soda can design, and we first are going to approach this in a very naive fashion. Namely, we want to find the right circular cylinder with volume 21.6563 cubic inches and minimal surface area, because it seems that if we minimize the surface area, that ought to minimize the amount of material being used. And 21.6563 cubic inches, that is the volume of a soda can. That is 12 fluid ounces or 355 milliliters, just changed to a cubic unit, namely cubic inches. Okay, so how do we do that? Well, we first have to find some formulas for cylinders, and the best way to do that is to visualize them. And what's a cylinder? A cylinder is made up of a bottom and a top and sides, and that's going to be important as we're finding the volume and area formulas for a cylinder. The cylinder has a radius and a height, and these two parameters completely determine the shape of the cylinder. And we've already gone through one step that is typically recommended when solving word problems, which is you want to draw a picture of the geometric situation, and then another suggestion that is typically implicit, which is give names to your parameters. You've got a radius and a height, you might as well call them R and H. Now the volume of a cylinder is always base times height. Well, the base is a circle. The area of a circle is r squared pi times the height, which is h. And what's the surface area of a cylinder? Well, that I'm not sure if you can find that in a formula collection. It's certainly not something that I would want to recommend to memorize. But remember that as we drew this thing, I said that the cylinder was made up of a bottom, which is a circle, a top, which is another circle, and a sides, which is basically a rectangle that's been rolled up. So the surface area is going to be the area of the sides, and the sides, remember, that's just a rolled up rectangle. That's length times height, and so it will have the height as a factor, and because the length is the circumference of the circle, the length will be 2 pi r. And then we have a bottom and a top, which both have area r squared pi, so you add 2 r squared pi to that, 1 r squared pi for the top, 1 r squared pi for the bottom. That's the surface area. Now we want to minimize that, and we see this is a function of two variables, r and h. Remember, pi is not a variable, pi is a symbol for a constant. Okay, well, we're only working with functions of one variable, but what we can do is we can use this constraint that the volume has to be a certain number and turn this into a function of one variable. And we're going to do that right here. The volume is r squared pi h, but it's also supposed to be 21.6563 cubic inches. And that means that our height is 21.6563 divided by r squared pi. I could have solved for either h or r and plugged that into the surface area formula, and I solved for h because that's going to make the computations a little bit simpler than they would be otherwise if I'd have to mess with square roots. Okay, we plug that in. We remember the surface area is 2 pi r times h plus 2 r squared pi. If we plug h in there for this h here, we end up with 2 times 21.6563, which is 43.3126, times r divided by r squared, so we divide by r, and then this pi over here, well, the 2 we already have, but the pi over here cancels with the pi over here, so this really is all that remains from the first term. The second term is still 2r squared pi, and here we see this is now a function of one variable. This is a of r, and we're considering on the domain from 0 to infinity. Of course, extremely large values for the radius are unrealistic. Extremely small values for the radius are also unrealistic, but the model will take care of that in and of itself, because we can already see from here when r goes to 0, the surface area goes to infinity. Infinity will not be a minimum, and when the radius gets large, then r squared goes to infinity, and again, infinity is not in the running to being a minimum. So the boundary values, the boundaries might as well be 0 and infinity. They're not going to be in contention for anything realistic here. Okay, now we do what we always do. We take the derivative, set it equal to 0. We take the derivative with respect to r. Here's where the Leibniz notation comes in very handily. d dr tells us that we have to differentiate with respect to r. So we get, well, the derivative of 1 over r. 1 over r is r to negative 1. The derivative of that is negative r to negative 2, which is negative 1 over r squared. And this ugly constant, we just copy it down. And the derivative of 2r squared pi is 4r pi, or 4 pi r. That one's a little bit easier. And if we set that equal to 0, well, we bring the negative stuff over, and I guess just flip sides. We get 4 pi r being 43.3126 divided by r squared. Bring the r squared over, we get an r cubed, and so r cubed is supposed to be equal to, after we divide by this 4 pi out front here, r cubed is supposed to be 43.3126 divided by 4 pi. And that means that r is the third root of 43.3126 divided by 4 pi. And yes, we use a calculator for that. That's approximately 1.5105 inches. If I say find the right circular cylinder with volume 21.6563 cubic inches in minimal surface area, I should have said find the dimensions of the right circular cylinder. The problem with that is I would have given away that we actually have to look for r and h, which is the first good leap in a problem that may well have been posed in industry at some point in time like this. And the other thing is, I would have needed so much room that I would have needed 3 lines for this headline, and then I wouldn't have been able to fit everything on one slide here. And as I've said before, we're limited with our board space here, and it's always good to see everything in front of you. Well, we've got the radius. We also need the height. And the height, of course, is 21.6563 divided by whatever the radius is squared times pi. That squeezes in right here, and of course you stick that in a calculator or a computer, and you end up with 3.0211, and again, inches. And here's where things get a little bit problematic, because that's not the shape of a soda can, because remember, the radius is half the diameter, so this proposed shape has diameter 3.02 inches, and it's got height 3.02 inches, so that thing looks more like a tuna can or a cube than like an actual soda can. So what's going on here? Well, that's what certainly I would ask myself also, and not being a conspiracy theorist, remember I may be crazy but not stupid, not being a conspiracy theorist, I was looking at this thinking, well, there must be something that I just didn't take into account here, and this is then also a very good teachable moment that I had at that point in time, and I followed up on it because, well, we probably haven't taken all the design parameters into account. And so what I did is I actually contacted a can manufacturer, and it turns out the actual problem that we would need to solve is to find the cheapest can, whatever that is, with volume 21.6563 cubic inches, so that the sides have a thickness of 0.041 inches, that the top has a thickness of 0.0093 inches, and the bottom has a thickness of 0.0113 inches, and that comes directly from design specifications in industry. And I am certainly very grateful to this major U.S. manufacturing company, as they would like to be referred to, who provided this image, which is their actual specifications for the can. You can see the top actually has a thickness of 0.0093 inches. That's the thickness for the top, and I call these things C because, of course, the thickness translates into a material cost. And I think the other two thicknesses really are on the next slide, so we're going to talk about that in just a second. The thickness themselves comes from the fact that the can has to resist a minimum 250-pound downward force as the lid is applied, because the way the soda gets into the can is actually the assembly line doesn't make cans right away, it makes cups. Then the soda is being poured in, and then the lid is applied. It is being pressed on with a 250-pound downward force, and because this lip here that fits into the lid is very, very thin. You have an immense amount of pressure on a very, very small area, and under these pressures, two metal surfaces will bond with each other in what in German you would literally call a cold weld, and it certainly holds up because, I mean, soda cans hold the soda and the internal pressure also, and so they bond like that, and so that is where you need a certain minimum thickness for the sides, and we'll see what that thickness is on the next slide. So strength is definitely a concern there. Thickness for the top then certainly is a concern because you want to have the pull tab in there, and the material on the sides of a soda can, no offense to can manufacturers, that material feels rather flimsy. I don't think you could put a pull tab on something that is that thin. It would just tear itself apart, and then you'd have sharp edges and people hurting themselves and all sorts of other things. So these are the kinds of parameters that in our first naive approach we certainly did not take into account, but that's also typical of a modeling process. You keep refining the model until you have something that is as close to reality as possible. So here the other design specs, just to show that I'm really not pulling this out of thin air. The side thickness is 0.0041 inches, and the bottom thickness is 0.0113 inches, and various other things like these fancy shapes are made for thickness as well as to make the can sturdier with using less material. The actual shape has been worked out by this can manufacturer, by this manufacturing company, using something called the finite element method, which is something that is developed in numerical partial differential equations, which is a course that is past the calculus and differential equations sequence that you are in right now, but we can still essentially say, yes, this design is still calculus based. What we're going to do is we're going to look at a right circular cylinder, and we're going to get at least very, very close to the industry specs. So let's look at a cylinder one more time. Remember, you've got a bottom, you've got a top, and you've got sides. Then you've got a radius and a height, which determines the shape. And the volume is r squared pi times h. The cost now, not the surface area, is what you get when you multiply the costs with the areas. So remember, the area of the sides was 2 pi r times h, because the sides are essentially a rolled up rectangle with height h and length 2 pi r. Actually, this is something that I often just demonstrate in class with a piece of paper. You've seen me shadow box quite a few times, so let's do this one more time. Well, these are the sides of a cylinder, right? This is just, if you look at it for the camera like this, that sort of looks like a cylinder. And if you were to just make a vertical cut down here, what you end up with is a rectangle. So that's how that comes about as a visualization. I probably should have done that on the first part of this presentation, but hey, we've got it here, and we see what we can do with this. Okay, so that's the cost for the sides, and then we have the cost of the top. Well, the top is, of course, a circle, so you get the cost of the top, or the thickness of the top, times r squared pi, times the cost of the bottom, also, plus cost of the bottom times r squared pi also. That ends up being, and note that I'm not going to stick these numbers, and I'm just going to go with C sides, C top, and C bottom until the very end. The volume is r squared pi h, which is 21.6563 cubic inches, and I don't want to mess with that number either. Remember that sermon about not dragging numbers through and we can work with parameters? Well, the height is volume over r squared pi, and that means the cost is cost of the sides 2 pi rh plus cost of the top r squared pi plus cost of the bottom r squared pi, which is, if I stick the height in there now, you end up with 2 times the volume times the cost of the sides. The pi cancels, and the r in the numerator cancels with the r squared in the denominator to give us an r in the denominator. And then we've got c top plus c bottom times pi r squared, because we can certainly factor this out. Then we want to take the derivative of the cost function with respect to the radius, set it equal to 0. We end up with the derivative of 1 over r, which is negative 1 over r squared, and the constant that we've got in the numerator here, of course, stays in the numerator there. And the derivative of r squared is 2r, and the remaining constants right here, of course, are also just copied down from the previous row. We set that equal to 0, so then we bring this term over, and we end up with 2 times volume plus cost of the sides over r squared is 2 times cost of the top plus cost of the bottom times pi r. The 2's ought to cancel, and the r squared should come over for an r cubed. Yes, and then you just divide by the c top plus c bottom times pi to end up with r cubed being equal to volume times the cost of the sides divided by the cost of the top plus the cost of the bottom times pi. And well, now we can just plug in numbers, right? Here's the stuff from the previous slide, and that I just stuck in the numbers directly and used the computer. That ended up being approximately 1.1112 inches. The height, same story. We just plug in those ugly numbers, and calculators are actually very helpful for that, because I wouldn't want to do that in my head. In fact, I can't. I wouldn't even want to do this with paper and pencil, even though I could. It would just be quite a pain. But the height ends up being 5.5830 inches. And if we look at that, well, let's see, what's the actual height? The actual height is 3.9 inches plus another ½ inch plus another 0.37 inches. Let's see, 0.53 plus 0.37, that's about 0.9. So the actual height is about 4.8 inches. Well, that's not 5.58, but not so fast. If we're looking at the radius is 1.1112 inches. So the diameter is about 2.2, while the diameter of the lid here is about 2.1. So that's actually pretty close. And then notice that here we've got these fancy shapes, which I was told by the engineer who gave me this drawing by mail, that these changes were motivated on one hand by the desire to have a sturdier can. So apparently this helps also resist this downward force, which you actually can try out. You can stand on a soda can if you weigh less than 250 pounds, and the soda can should hold you up. Now, if it crushes under you, that just means you didn't quite hold still. I've crushed soda cans with my feet, and some people crush them against their heads, even though I don't know why they would want to do that. So that doesn't mean you're overweight. That just means that you applied a kind of pressure that the soda can was not meant to withstand. But that also means, and another reason for this thickness change and these fancy shapes here, was that you would save materials, because when you make the can wider, you need less height. So having an actual can that is less than 5.58 inches tall, that makes sense based on this more sophisticated model, right? And then also look here, this is not quite the diameter, because the actual diameter is farther out, and we'll see that in the next image. And again, I am very grateful to this company that provided these images to me, and they just want to be referred to as a major US manufacturing company. If we're looking at the other one, the actual plug diameter is 2.258, which is a little bit more than the 2.22 that we computed, so that is actually really good. And well, that pretty much ends this presentation. What have we seen? We have seen that the methods of elementary calculus can get us, if not the exact solution, which requires sophisticated methods that I would actually have to talk to colleagues about how to execute them. It's not my research area to do the finite element method, but we can at least come really, really close with the methods of elementary calculus. And that is very nice, because this problem that we have discussed here in this second part of the presentation, apologize for the interruption again, this problem that we have discussed in this second part of the presentation is a very real and a very important economical as well as ecological problems. So, anytime you think about calculus, if you can't think of anything else, by this time you have solved at least one very real problem, or you have gotten at least very, very close. And certainly in your science and engineering classes, you will take this places that I have never seen and may never see, but that's good. You want to be ready for this stuff. Somebody knocks. We are done with this presentation anyway. I'll see you next time.